final video on probability, and we're going to look at tree diagrams as just another way to help us answer questions, another way to represent what's going on. And you will remember tree diagrams from last year and from GCSE, but I want us to think first of all very carefully about what's happening along these branches and what events we're actually working out on each branch. So let's imagine we're talking about event A in the first pair of branches and event B in the second pair of branches. So this branch represents the probability of A occurring, and this one we know represents the probability of A not occurring, or remember we called that the complement of A. Now, it's very tempting to think here I'm going to write the probability of B and probability of not B, B, not B. But that's actually not what's happening on these branches, because here this is the probability of B occurring given that A has occurred, because we followed the A branch, so we know that A has occurred. This, therefore, is the probability of B not happening given that A has happened. So now, this pair of branches, we are given that A has not happened because that's what we followed to get here. So this is the probability of B occurring given A has not occurred. And this is the probability of B not occurring given that A has not occurred. Now, what happens at the end of the branches then? If you follow this branch and this branch, you end up with the probability of A happening and B happening. Now let's think about the last video for a second. This is interesting because in the last video we had given that formula, which was the probability of B given A is the probability of the intersection. I could write A or B or B, A, B the other way. Start again. I could write A or B either way around, and for the intersection it doesn't make a difference. But here we have to have the second one, the probability of A. Now, if I rearrange this by multiplying up, we have that the intersection is the probability of A multiplied by the probability of B given A. Now, think about what happens on a tree diagram as you move along the branches. You multiply. So A here multiplied by B given A there gives us the probability of A and B. So actually a tree diagram set up properly is just another way of representing our multiplication formula for B given A in a visual way. So let's just fill in the rest of these. This branch is the probability of A happening and B not happening, the intersection of those two. This one is the intersection of not A and B, and this one is the intersection of not A and not B. Now, the textbook doesn't mention this, but I just want to consider a couple of things briefly. Where on this diagram is the probability of B occurring? Now, the probability of B occurs in two instances on this diagram. It occurs here and here, because both of these have B occurring, one with A occurring, but one with A not occurring. So the probability of B occurring would be the sum of these two. And similarly, where is the probability of B not occurring on this diagram? Well, B doesn't occur here and it doesn't occur here. In one case, A has occurred, and in the other case, A has not occurred. So the probability of B not occurring is the sum of these two here. So let's have a look at example 8. We are told that there is a bag that contains 6 green beads and 4 yellow beads. A bead is taken at random from the bag. The colour is recorded, but then the bead is not replaced. And you'll remember these kinds of questions from GCSE. Where there's no replacement, we know that the probabilities change on the second branches. We're told that the second bead is taken and its colour is recorded. And then we're given some information and a question to answer. So before we do anything else, I'm going to fill in this tree diagram. We have that the probability that the first bead is green would be 6/10. The probability that the first bead is not green, or yellow in this case, in fact let's just use yellow instead of not G, the probability that it's yellow would be 4/10. Now, given that we have taken a green, what's the probability that the second bead is green? Well, there are now only 5 green beads left and there are only 9 in total. This branch says, what's the probability that given the first was green, the second is yellow? So we know there are 9 beads, but there are still 4 yellows. And note that this pair of branches adds up to 1, as it should do. So coming here then, now we are given that the first one was yellow, what's the probability that the second one was green? Well, we're still out of 9 beads, but this time the first one picked was a yellow, which means the second one picked will be out of the 6 remaining greens. And here, what's the probability that given that the first was yellow, the second is also yellow? So we're out of 9 beads, but there are only 3 yellows left because we've taken 1 in our first bead. And again, notice that these 2 add up to 1. Now let's write a few of these down at the end, shall we, just to help us answer any subsequent questions. We don't necessarily need to do this every time, but I want to just for the sake of this example. So the probability of having a green and a green here, we know we're going to multiply these 2 together. So we have got 30 90ths. Here we have the probability of a green and a yellow, and that's going to be 6 4s are 24 90ths. Here we have the probability of a yellow and a green, and that's also going to be 24 90ths. And here we have the probability of a yellow and a yellow, and that's going to be 4 times 3 is 12 90ths. And I'm always going to check that these sum up to 1 to make sure I've not made a mistake. So if we just quickly check 30, 24, 24 and 12 make 90. So we have 90 90ths going down there. Now, having done all of that, I've got a complete probability tree. I'm now going to answer the question. So the question says, what's the probability that both of them are yellow given we know that they are the same colour? Let's write this using our line notation. What's the probability that both are yellow given that they are both the same colour? Now, I want you to think about your formula again for A given B. Let's make a little note of it just out the way here. The probability of A given B is the probability of both of them over the probability of the second, because we reduce our sample space to the second, don't we? So here, in terms of what we're thinking about here, both of them, we're saying what's the probability that they are both yellow and at the same time both the same colour. Now that's kind of bizarre to think about, but actually that's just the probability that they are both yellow, isn't it? Because both yellow is also both the same colour, so that's fine. But then that's out of the second one, the probability that they are both the same colour. So let's put our fractions in. The probability that they're both yellow and both the same colour is 12 90ths. And that's out of, let's just make sure you can see exactly what I'm referring to there. Both yellow and both the same colour is this one. Out of the probability that they're both the same colour. Well, both the same colour would be yellow, yellow, but it could also be green, green. So we have got 12 90ths or 30 90ths. So we have 12 90ths out of, the denominator here is 42 90ths. That would simplify, of course, to 12 out of 42. You could just jump to your calculator here, but that's no problem. I could simplify it, but I don't have to. 12 out of 42 is 2/7. So either of those answers would be acceptable. So you need to make sure that you're happy with what the different branches of the tree diagram represent, and make sure that you are happy with the formulae for given that and for the addition that links the union and the intersection from our last video. And you can now have a go at exercise 2E, and that is the end of the chapter.